Welcome. This is Unit 2, Lesson 7, and we are going to work with rational exponents, which are exponents that are fractions, and sort of going back and forth between radical form and rational exponents. And this first table here, I'm only going to work on this first kind of row here across. And these are all values that we can put in the calculator. If we put 9 to the 1/2 power, okay, that should give me 3. Okay, if I put 8 to the 1/3 power in the calculator, I should get 2. And if I were to put 27 to the 2/3 power, I should get 9. All right. Now, if we move over to the right here, okay, if I do 9, or the square root of 9, I should get 3. Okay, that kind of same thing I get here. If I do the cubed root of 8, I should get 2. Okay, it's the same thing here. And if I do the cubed root of 27 squared, I should indeed get 9. So you can see that there's kind of a relationship between our fraction, okay, highlighter time, between our fraction and our radical and their numbers, the root and the exponent. All right? And once you see that, it becomes really easy to understand. So what is that connection or correlation? All right, here's a little phrase that I like to throw down to my kids here. Top down, bottom out. Top down, bottom out. What do I mean? Well, let's take a look at a couple of the examples they give us here, and I will show you exactly what I mean. So there's a pattern relating fractional exponent expressions to radicals for expressions. Okay, express 34 to the 1/2 in radical form. Let's start with that one first. If I have 34 to the 1/2, that they want in radical form. Well, my base is going to stay the same, 34. And by top down, bottom out, what do I mean? The top just comes down, okay, and the bottom shoots out, okay? You see what I'm saying? So the top, which is the numerator, came down, it slid down and becomes the exponent. The bottom, which is the denominator, out, that becomes the root, okay? So that's where I get top down, bottom out. Now, if you want to, some people just need, you know, just give it to me straight, Visca, how does this work? Your numerator, okay, your numerator stays with your base, and your denominator becomes your root. I just like to say top down, bottom out. Easier to say, makes you visualize it, the actual process, but the denominator is your root, and the numerator is the exponent with your base. Okay, but this works both ways. So let's take a look at the second one they want us to do. Take the cubed root of 3 squared and write that as a fractional exponent. All right, and wow, exponent is spelled wrong. Exponent. So if I have the cubed root of 3 squared, right, top down, this is bottom out. This is top down. All right, hey, look at that. Thanks, Miss Vona, for that awesome thing. Let me turn off my email here. All right, my email's turned off. So it's top down, bottom out. The bottom came up. This is the bottom of my fraction. That's my denominator, right? So if I rewrite my 3 with a fraction, the bottom came out and the top slid down. That was my numerator, right? That's the same thing. Okay, so it's real easy to go back and forth now. Top down, bottom out. The denominator is my root. The numerator just becomes the exponent for my base. Okay? Pretty simple. Now, before we start doing math operations, okay, with radicals or with fractional exponents, or rational exponents, that's what, you know, please know that rational, that's the same thing as saying fraction. That's just a math term that means fraction. And you might be saying, isn't fraction a math term? Yeah, we came up with another math term, rational, to represent a previous math term, fractions. Crazy, I know. But like I always say, math people like to come up with things to make themselves feel and sound smarter. So instead of saying fractions all the time, they say rational. What the hell is rational? I don't know, but it sounds smart, doesn't it? Let's start using it for fraction, Bill. And that's how these things start. Okay, so a lot of these things should be reviewed. Some may or may not, but this should be a review for Algebra 1. So if I am multiplying a common base here, a, okay, we're doing this first one, and it has exponents. I add the exponents. So a to the m plus n. That would be my result. So for an example here, if I had x squared times x to the 10th, that would give me x to the 12th because I add those. Pretty simple. All right, let's try the next one. If I have an exponent raised to an exponent, okay, I multiply my exponents together. That's a times m times n. Okay, so that's a raised to the m times n. So if I have x squared raised to the 10th, that gives me x to the 20th because I just multiply my exponents. All right? Now, this happens a lot. This throws people off, and I'm glad we have an example like this. If I have an expression with more than one, I don't want to say term because there's no plus or minus in there, but there's a coefficient and a variable or two variables, and they both have one exponent that applies to both of them. Well, this is like a to the first, b to the first in parentheses, times m, isn't it? Don't I multiply exponents when they're raised to exponents? So I'm really going to multiply my m times both of those. That really ends up being a to the m, b to the m. Okay, that exponent applies to both of them. Okay, so let's give an example here. Let's say we have x squared, y squared to the 10th. Well, that'll give us x to the 20th, y to the 20th. Let me give you another one here with a number. Let's say I have 4x cubed squared. That square applies to everything. You can say, oh, 3 times 2 is 6, so it's x to the 6th. The 4 also gets squared. Technically, that's 4 to the power of 1. I need to square my 4 and my x term, okay? That's something that trips up people all the time. So just be aware that exponent applies to everything in parentheses. All right? Okay, let's go on to the next one. Oh, negative exponents. They are huge. They are important. They are important in pre-calculus and calculus, all that jazz. They don't go away. Sometimes I wish they would, but they don't. All right? If I have a negative exponent, I need to make that exponent positive. Technically, I have a fraction. Everything that I have is a fraction. I can put that over 1, and it's a fraction. Or it is a rational expression now, isn't it? Look at me go. In order to make a negative exponent positive, I take the exponent and whatever it's connected to, and I flip it. Okay? This happens to be in the numerator, so I'm going to bring it down to the denominator. If it were in the denominator, I would bring it up to the numerator. That's what I mean by flipping it. So technically, there's a 1 out in front, right? We don't bring the 1 down because my negative m is only connected to the a, so I only bring the a down. My 1 stays on top, and I have a to the m on the bottom. That's it. That is it. So let me give you a couple of examples here for this one as well. Okay, I'm going to erase some of this for the sake of room. If I have 4x to the negative 2, okay? That's technically over 1, even though I don't write it. Technically, it's over 1. The negative 2 is only connected to the x, all right? So that would be 4 over x squared. There you go. Let's do another one here. Okay, I'll do this one in green. Let's say I've got 3, then in parentheses, x, y to the negative 2, all over 4c to the negative 1. All right? So anything with a negative exponent needs to flip. That means this flips down here, and I actually have something in the bottom of the negative exponent, that's going to come up. So when everything is all said and done, my 3 and 4 stay. They don't have the negative exponent, right? I have xy squared, and then I have c to the first. That comes up here. If I want, I can distribute that 2 exponent in the bottom, so I can say 3c over 4x squared y squared. All right, so if you see a negative exponent, you flip it and make it positive. You'll have to do a few of those just to feel a little bit more comfortable with them, but you'll get there. It's easy. Next one, next one. If I am dividing two things, okay, common bases, we subtract their exponents. M minus n. Subtraction order matters. So please note, it is top minus bottom, okay? Although, I'll be honest with you, I like another way to do this, and I will show you in a second. So an example, if I have x to the 10 over x squared, I subtract them, and I get x to the 8. All right? That's one way of doing this. All right? The second way is just simplifying your fraction, okay? If I have the same problem, well, 2 of these x's cancel with 2 of these, and I end up with 8 left. That's why this works. I just like to cancel. How come? Because if I have a bigger numerator in the bottom, let me flip that. If I have x to the 2 over x to the 10, if I subtract them, okay, let's do this way subtraction. It's x to the 2 minus 10, that's x to the negative 8. Of course, that's over 1, so I need to flip it. I end up with that. Okay, it's not bad. But if I do my reducing, okay, if I can reduce it, 2 of these cancel with 2 of these, and I end up with an 8. Well, this was a 1 here. I really only have 1 step instead of 2. So if you can reduce, sometimes it's easier. Other times, you really just need to subtract. But they are one and the same. All right? Now, on to the next one, okay? On to the next one. Again, that m needs to apply to everything in the parentheses. So that's a to the power of m, b to the power of m, okay? Exponents are like square roots, okay? If I have a fraction raised to an exponent, that's numerator raised to the exponent, denominator raised to the exponent. Same thing with radicals, right? If I have the square root of a over b, that's square root of a over square root of b. This works both ways. It goes both ways, okay? And how come this works? Because technically, that's a over b to the 1/2. Isn't this 1 and 2? 1/2. So that's a to the 1/2, b to the 1/2, which is radical a over radical b. Square root. Remember, square roots, right? The big thing is, wow, look at that. That was a nice parabola. Bam, bam. So, if you have an exponent and a fraction, okay, that exponent applies to the whole fraction. You need to apply it to the top and the bottom. All right, and this last one we just learned today, it's what our notes are about. Top down, bottom out. Top comes down, bottom is out. Done. Okay, I don't think I need to give you an example of that. We just went over some in that box, and we're going to do some more in a little bit. Okay, so let's try some of these. Let's simplify some of these. All right, and we're going to have to use our previous knowledge on how to simplify radicals. Okay, some will work out nice and easy, and some won't. Let's see what is what here. Okay, if I have 216 to the 1/3 power, that's like saying the cubed root of 216 to the power of 1. All right, and actually 216 is a perfect cube. That's 6. We're done. Okay, if you want to try some of these, go ahead. I'm about to rip through them. Now, b, that is the cubed root of 40 to the power of 1. 40 to the power of 1, of course, is 40. So we're really taking the cube root of 40. So remember how we're going to break these down. The biggest perfect cube that goes into 40, I know what that is, 8. 8 times 5. They are both under cubed roots, and the cubed root of 8 is 2. I can do nothing more with this, so I leave this cubed root of 5. And I put that in parentheses. Done and done. All right. C. Okay, that's cubed root. That is the cubed root of 8x cubed. All right. That's the cubed root of 8 times the cubed root of x cubed. Oh, this works out perfect. That ends up being 2x. Bam. Oh, boy. Okay. Okay. So let's do this. 54. All right. So this cube has to apply to every, even that's a power of 1. So I have 54 to the 1/3 times x. Okay, 6 times a third is 2. That's nice. That works out. Times y. 5 times a third is 5/3. All right. So really, I've got the cubed root of 54. X squared, that's done. The radical went away. And this is top down, bottom out. Okay, so I really only need to simplify my cubed root of 54. All right. And I know the biggest perfect cube that goes into 54 is 27. So it's 27 times 2. They're both cubed roots. The cubed root of 27 is 3, and there's nothing more I could do with this. So I'm done. Times. I have my x squared times. Again, this is division, in case you forgot. 5 divided by 3, it goes in once with the remainder of 2, which means 1y comes out, and the remainder, 2, remains in. And now it just comes to a point where I write everything outside of the radical together. 3x squared y. And then everything that's still in a radical will stay there. 2y squared. Okay, so again, this is a review of also simplifying radicals. This all ties in together, okay? This helps you really get a solid, a grasp on the foundation, okay, of radicals. This is really good. Really good stuff, people, really good. All right. What are the 5th root of a and the 5th root of b cubed in exponential form? If you want to pause the video and do this on your own and figure these two out, they're simple. I'm going to do them right now. The 5th root of a, and technically that's a to the power of 1. If it's not written, it's 1. Top down, bottom out. The bottom was what went out. The top's what slid down. There you go. Exponential form. That is a form with an exponent, not a radical. That's what this means, exponential form. I want an exponent, not a radical. All right, so let's do this. 5b cubed. It's a 5th root. Top, down, bottom, out. The bottom is my 5. The top was my 3. Done. You're smart. You are smart. All right, let's go on to the next one. I love me some space in the cosmos. Example 4, Kepler's third law of orbital motion shows how you can approximate the period P, which is in Earth years, it takes a planet to complete one orbit around or of the sun. Use the function P equals D to the 3/2, where D is the distance from the planet to the sun in astronomical units, AU. Now, an astronomical unit is 93 million miles. That's the distance from the Earth to the sun. When they measure things in space, they use AUs. They don't use miles. So instead of saying 930 million miles, they'll say 930, or excuse me, they'll say, 100 AUs. Oh, 10 AUs. Look at me go. 10 AUs. All right. Don't worry. You can play around with that number yourself. It is 10. But this is all like useless information they're giving you here. They really give you a lot of stuff that's not really important to solve this problem in this word problem, which is what word problems love doing, which is why people hate word problems. So, how many Earth years does it take Mars to orbit the sun if Mars is 1.52 AUs from the sun? Now, How many Earth years does it take for Mars to orbit the sun? P, that's the period. In Earth years, it takes a planet to orbit the sun. This is my equation. P equals D, which is the diameter, to the 3/2. We want P. How many Earth years does it take Mars to orbit? That's the P. That's what we're trying to figure out. If Mars is 1.52 AUs from the sun, so D is the distance of the planet to the sun. Okay, Mars is 1.52 AUs from the sun. That's D. So really, P equals 1.52 to the 3/2. That was really easy. We just had to break it apart. I mean, now the only reason I think they would give you this information right here is if they wanted you to convert it to miles afterward. Okay, they don't. Okay, they want it. Okay, how many Earth years does Mars take to orbit the sun? You're going to find out what P is, and P is in Earth years. So we're good to go. So all you need to do is you need to take, let me quit this right here. Yeah, actually, probably, there you go. And I want to take 1.52, and I'm going to raise that to the 3/2. And I'm going to get approximately 1.87. So that will say the period is approximately 1.87, and that answer should be in Earth years, right? There you go. That's it. It took longer to read that and dissect it than it did to do the math. And, you know, such is the way of the word problem. So we're about 22 minutes in. I'm going to stop here. You'll see, if you want, you can try some of these on your own. We've got some graphing coming up, all right? But you know what? Try some of these on your own, and then you can come back and check them to see if they're right on Unit 2, Lesson 7, Part 2 video, which will be coming up next. See you later. Have fun. Stay warm because it is frigid cold right now here in upstate New York. Whew. See ya.